Welcome, chapter 6. And we're only going to be doing two sections, 6.1 and 6.2. Okay, so 6.1 and 6.2 are both about what we call probability distributions. And that's why we skipped over chapter 5. Chapter 5 is just about probability. So if you've taken college mathematics, which I believe you should have because it's a prereq for this class now, I think. You should have done some probability in college mathematics. So nothing crazy there. This kind of continues that a little bit, but not in a sense that we really need to go through chapter 5 to have all this information. Okay, so probability distributions. Let's talk about what those are. And so 6.1 is just kind of like a general overview. And then 6.2, we really dive into probability distributions. So probability distribution, some things that you should know. It helps us keep track of the outcomes in a random experiment. So it lets us know what are all the outcomes in the random experiment and the probabilities associated with each one of those outcomes. So it does two things. It tells us all the possible outcomes, and it shows us that. Okay. And it gives us the probabilities for each one of those outcomes. So, like, for instance, if I'm flipping a coin, a probability distribution for flipping a coin would show you the outcome heads. It would show you the outcome tails, because those are the only two outcomes. And then it would show you the probability for those. And of course, this is in an experiment. Okay. But if we did an experiment and everything worked out nice and neat for us, then hopefully you would see the probability for heads be 0.5. Okay. And again, they're going to give us the probabilities as those decimals, just like when you were doing frequency or relative frequency. Relative frequency was basically showing you the outcomes as their decimal percentages, as their probabilities. Okay. So relative frequency and probabilities, they share a close relationship. Okay. So the probabilities, again, that you'll see in this, they're not going to be fractions. They're not going to be the percentages. They're going to be the decimal of the percentages. So heads would be 0.5, tails would be 0.5. Okay. Some other things about probability distributions. What I gave you was an example of one type, but there are two types of probability distributions, and they're going to be numerical variables for us. Okay, numerical variables generally when we deal with the probability distributions, and those two types of numerical variables are going to be discrete outcomes, meaning that we can list them or count them. Okay. So the flipping of the coin is a type of discrete outcome. You're either going to flip heads or you're going to flip tails. Okay. You're either going to flip heads or you're going to flip tails. Rolling a die. You're either going to get a 1, a 2, a 3, a 4, a 5, or a 6. That is a list, or we can count them. Okay. The other one is what we would call continuous outcomes. They cannot be listed or counted, but occur over a range. Example of this, height. A person's height is over a range, because technically if I say that I'm really 5'10" or 5'11", I'm somewhere between there actually. My height is not exactly 5'10". My height is not exactly 5'11", but I'm in somewhere in there. Okay. So a person's height is not exact. It's actually over a range of values. Okay. The same thing with weight. A person's weight is over a range of values. I could say that I'm really 90 pounds. Obviously, I'm not 90 pounds. I'm just making this up because I don't want to tell you my real weight. But if I say I'm 90 pounds, I'm really probably somewhere between 90 and 5,000 pounds. Okay. Again, I'm not exactly 90. I'm not exactly 5,000. I'm somewhere between there. Okay. So your weight is generally over a range because I can't count it, and we can't list all those. And again, we're talking about in an experiment here, and we want to try and be as accurate in an experiment as possible, which means we're going to have decimals. Okay, so it's going to be over a range. So here we're really going to kind of dive deep into a lot of numerical, and we're going to be talking about discrete and continuous. 6.1 is more about the discrete, and 6.2 is more about the continuous and how we deal with those. See here, and last but not least, a couple pieces of information. Probability or discrete probability distributions can be given as tables, graphs, or equations. Okay. Probability distributions can be given as tables, graphs, or equations. Continuous probability distributions are given as an area under a curve. And if any of you decide to ever take calculus, you talk a lot about an area under a curve. And so continuous probability distributions relates a lot to calculus. Now, we are not going to be doing any calculus. Do not fret, even though I said the word calculus. We have technology to help us out. So anything about dealing with the area under a curve, we're going to have technology and things help us out. So don't freak out about that. Also, please know that when you do a discrete probability or even the area under a curve, that when you add up all the probabilities, it should equal 1. The total area under a curve is 1. All the probabilities from each discrete piece add up to 1. Remember that example of the coin flipping heads and tails. 0.5 plus 0.5 is 1. Okay? If I did it with the roll of a die, the probability of each die roll is, sorry, let me get this real quick, just doing it on my calculator. 0.16 repeating. If I take 0.16 repeating and add it all up, I get 1. Okay? 6 times. 0.16 repeating plus 0.16 repeating plus 0.16 repeating. Add that up 6 times, you get the number 1. Okay? So that's important to know. All right. So let's take a look, I believe, at what you're kind of going to be seeing in your assignment and things like that. Okay, so the directions were here. I've got 2 ideas, and I just want to know, are they continuous or are they discrete? So just recognizing what kind of variable you have. So it says the time in seconds it takes for light to travel from the sun to the earth. Is that continuous or discrete? And then part B says the number of planets in our solar system, continuous or discrete. And pause the video and go. Okay, so for the first guy, part A, hopefully you said this is continuous. Okay? Because light traveling from the sun, it's in seconds, and it's probably pretty fast, but there are different, the light is traveling from different places on the sun, which means that each, I guess you could think of, light beam that comes to Earth, it's going to get here in amount of time that's over a range. Some of it will get here really quick, like in 1 second. Some of it might take just a little bit longer, like 1.05555555. You see how that's kind of a continuous range. I can't necessarily list or count each possible outcome. It's impossible. Now, when you look at B, hopefully you said this is discrete, because the number of the planets in our solar system, we can count that up. And we even have the name for each one of our planets. Now, I know that number keeps kind of changing, but it is very much discrete. It is concrete. It is either we have 9 planets or we have 7 planets. Okay? So there you go. One of your problems is going to be like that. Well, actually, a couple of your problems are going to be like that. Is it concrete? Or sorry, is it continuous? think like, can it have like multiple versions of decimals? That's generally how I think continuous. There kind of can be decimal type answers. And or is it discrete, where it's this or it's this? It's hard, fast, numbers like 1, 2, heads, tails. If you're thinking about like in the game of life, there's a spinner that has colors and numbers on it. Did I spin purple or did I spin green? Things like that. Just kind of giving examples of like discrete versus continuous. All right. So here's a probability distribution. We abbreviate probability distribution PDF. Okay. Probability distribution function. That's what the F stands for. Probability distribution function. Okay. That's what the F means. So with that, and sometimes we also call it probability density function. Okay. So probability density function, probability distribution function is PDF. All right. And I think I had that on the first screen. Let me see here. No, I didn't. But just know that that is an abbreviation for it. So it says a magician has shaved an edge off of one of the 6 sides of a die. As a result, the die is no longer quote unquote fair. The figure below shows a graph of the probability density function or the probability distribution function, PDF. Okay. So it says show the PDF in a table format and list out all 6 possible outcomes and their probabilities. Okay. So they basically just want you to turn this into a table. So go ahead and do that. Turn this into a table for me and go. Okay. So obviously, I mean, just talking about this is obviously discrete. If it was more continuous, this would look like a curve or a type of histogram. Okay. It'd be very fluid in here, and all these would be connected to each other. All right. So you'll see more of that coming up later on. So we just want a table. So we have 6 outcomes, 2 columns. So I really need 7 2 columns and 7 rows. Okay, because I want to label what my stuff is. So that's why I have the extra row. Okay, so I would call this outcomes. Oops. And let's call this probability. All right, and I like to center these things up. Let's make all this center. So down below here, outcomes. Well, there are 6 outcomes. You can see them right there. You have 1. Oops. Go back and fix that. I don't want it that big. There we go. 1, 2, 3, 4, 5, and 6. The probabilities, you just go back up and look at it. Okay? So the probability for 1 is 0.10. The probability for 2, and the same thing for 3, 4, and 5, is 0.20. So 0.20, 0.20, 0.20, 0.20. And then 6 is the same as 1. So it's 0.10. And there you go. Okay? So that's all they wanted you to do. Take the picture and turn it into a table. See? Easy peasy, nothing crazy. Sometimes in here, they'll want you to give us the fraction. So the fraction, just kind of just throwing it in there. And you just have to read the fine print to know. So 0.10 is 1/10. 0.20 would be 2/10, which would be 1/5. So now you know what the fractions of everybody down below would be. Sometimes they ask for the fractions. Sometimes you'll just give them the decimals. Read the fine print. Okay. They will also, let me see if I did this. Yeah. So they will also ask you to do the reverse of this. Okay. And sometimes they might say, take this table and turn it into a graph. So all you do is you just take the table and reverse it, which is something like what you're going to do in this. Okay. So in here, it says when a certain type of thumbtack is flipped, the probability of it landing up means the point is up is 0.6. The probability of it landing down is 0.4. Okay. So now it says, now suppose we flip two such thumbtacks, one red, one blue. Make a list of all possible outcomes, arrangements, using U for up and D for down. List the first one as the red, and so the first tack would be red, and the second tack would be your blue one. So this would be red, then blue. Okay. Include both UD and DU because these are two different outcomes. Remember, this is the red tack, this is the blue. This is the red, this is the blue, even though both of them kind of are the same idea. I want you to find the probability of each outcome and record it in a table. All right. But we could also turn that into a graph as well. So go ahead, pause this. And what I want you to do is I want you to make the table of this and I want you to make the graph of this as well. So pause and go. Okay. So there are actually four possible outcomes. There's UU, DD, UD, and DU. So I need a 2-column, 5-row chart because we're going to talk about its outcomes. Okay. Excuse me. So outcomes, probability. Okay. All right. So I want to center these up actually. Let's select, oops, nope, not moving. There we go. And let's make sure everything's center. So the outcomes we just talked about, UU, ED, UD, and EU. Okay. So how we figure these out? Well, if you remember a little bit about, if you remember a little bit about college mathematics and figuring out probability, we want to know what is the probability of U and U. And since these are independent events, really what you're doing is you're just going to take the probability of the red U, so the red tack U, times the probability of the blue tack U. Okay? So that's how we're going to figure these out. And we know the probabilities for up. Up is 0.6. Okay? So all that's going to happen is you're just going to go to your handy dandy calculator. You're going to take 0.6 times 0.6. Okay? And 0.6 times 0.6 is 0.36. So there's the probability. Oops. That's not what I want. I want to be inside my chart. 0.36. And then you basically just continue the same fashion with DD and UD and DU. Okay? So the probability of DD was 0.4. So if I take 0.4 times 0.4, I get 0.16. UD and DU will actually have the same probabilities. So I just need to multiply the probability of up times the probability of down. So 0.6 times 0.4. So when I multiply those, I get 0.24 and 0.24. And it says right here, all the probability should add up to 1. So if I go to my calculator and take 0.36 plus 0.16 plus 0.24 plus 0.24, I do end up with 1. So there's the table. That's what they were looking for. Now, I also asked you to extend this and make a graph of this because I want you to experience this. And this is discrete information. So if I make a quick graph, and I can do this pretty easily. So just like before, over here, this information is the probability. And down here are the outcomes. And I've got UU, ED, UD, EU. I'm going to move them where they need to go. And then I just need to kind of label my side over here. So let's see here. What do we got? Looks like everything's kind of going by fours. Okay, like 0.04. So if I kind of count that up, this guy would be 0.04. Then I would have 0.08 and then 0.12, 0.16, 0.20, 0.24, 0.28, 0.32, 0.36. And then I can make my little quick graphs. Okay? So we got 0.36. Wow, that's horrible. Let's see if I can do this a little bit better. We'll just use this. 0.36. The next one was 0.16. UD and DU both had the same, which was 0.24. And your table can be in any arrangement that you wanted, just so you know. I just put it in this order, going by what was on my table up above. I probably put that one a little bit higher than what I should have, but that's all right. You get the idea. So you can easily take tables and turn them into graphs and take graphs and turn them into tables. Nothing crazy there. Okay. And a little bit of review from college math right there. That's kind of like why I chose this problem, so we can review that idea. And there you go. See, nothing crazy. All very straightforward. Okay. Like I said, 6-1 is a lot about discrete. All right. So here, this is one of those continuous ones, although it's not really curvy and things like that. But this is a continuous because we're talking about the depth of snow. Okay. So we're talking about the depth of snow. And the depth of snow is very, very continuous because we don't exactly, I mean, like they say we're going to get, when the weather, okay. So some of you might have experienced this, some of you might not have. From me being from Kansas City, Missouri, I've experienced snow and ice and all that stuff. So when I've watched news reports before, weathermen would usually say, hey, expect 1 to 2 inches. See, that's a very continuous answer because I could get a little bit less than one. I could get exactly one. I could get 1.5 inches. I could get 1.33333 inches. See, that's a very continuous type of response there that they were giving us. Just like down here when it says rain, expect 1 to 5 inches of rain. That's a continuous answer. And that's what they're showing you here. This is what a kind of a continuous answer looks like. Again, in 6.2, we're going to look a lot more at these continuous type answers. But this is a continuous answer for what's going on here. So let's take a look at this problem and let's explore this together. So it says, Eric wants to go skiing tomorrow, but only if there are 3 or more inches of snow. Okay? According to the weather report, any amount of new snow between 1 inch and 6 inches is likely. So that's why you see this. From 1 to 6, it all has the same probability of happening. We have a 20% chance of 1 to 6 inches of snow. Okay? Or 0.2. The probability density curve, or you can call this a probability distribution function, because that's what this is, a PDF. For tomorrow's new snow depth is shown. Okay? This is a continuous one. Because notice how it's not just, it's not just that 1 or 2 or 3. That when it snows, it doesn't say, oh, I hit 1 inch, done. Snow doesn't do that. Or when it snows, it doesn't say, oh, 4 inches exactly, stop snowing, everybody. The clouds don't communicate like that. And if they do, that would be weird. I would be frightened for my life with clouds communicating the weather. So from here, it says find the probability that the new snow depth will be 3 inches or more. Okay? So remember that this is all about the area under the graph. Okay? The area under the curve. Right there, I am telling you how to find the probability for this. The key word, area. So we want to know what's going to happen from 3 or more inches. We want to know this probability. Hey, what does that shape look like? Oh my gosh, this shape looks like a rectangle. Ah, that's a circle. I want a rectangle. Do we know how to find the area of a rectangle? Absolutely. Length times width. So what is this length here? Well, it goes from 3 to 6. So that's 1, 2, 3. What is this width here? Well, it goes from 0 to 0.2. So what is the probability? So now that we got that information, what is the probability of 3 or more inches? All we're going to do is find the area of that little rectangle, which is 3 times 0.2. And if you take 3 times 0.2, you get 0.6. Okay? So the probability of Eric going skiing tomorrow is about a 60% chance. Because 0.6 as a percentage is about 60. Cool? Yeah. See, we don't need calculus. Technically, in calculus, you could do that, but it's all about the area under the curve. In our case, our curve here helped us form a rectangle, and we just had to do length times width because that's how you find area of a rectangle. I think I have one more. Nope. That's it. So that's what you're going to be seeing in your assignment. So 6.1 covers questions 1 through 18. All right. Catch you later.